Good afternoon, everyone. Welcome to the RemedX presentation on the treating of solvents in soils with in situ deep soil mixing. I'd like to go through a bit of housekeeping with you. Pete, if you can just go through, please. So just to remind you all that all attendees, your microphones are muted throughout the webinar, but you are able to send questions through to us. You can post online, and there'll be a Q&A session at the end of the presentation. We will obviously try and endeavour to answer as many questions as we can, but there is obviously a time constraint, so if we can't, we will then post them later. Shortly after the webinar, there will be a link to a short survey. If you could take a few minutes to provide some feedback, please, and then that would hopefully allow us to improve the webinars going forward. Thank you. Pete. So I'd just like to go through who you're going to be listening to today. So there's myself, Richard Martin, Associate Director at RemedX, have approximately 25 years experience. Pete Finden is also an Associate Director based in Manchester, again has Associate Director, is responsible for client development, delivering remediation design, system installation, operations. He's got over, again, 25 years experience in the UK market. He's worked on projects in Australia, New Zealand. Pete's got great experience really in soil groundwater remediation, using a whole variety of technologies and techniques. Also, in addition, is our colleague Lawrence Smith, principal scientist. Lawrence is as chartered scientist, has about 10 years of experience working in contaminated land. Lawrence has also worked on a huge number of projects, not just in the UK but around the world, with Madeira, Iraq, South Africa, Tanzania under his belt as well. Lawrence generally kind of works with tender scoping, design, completion, site operations, maintenance, site management, project management, but is also one of our key members when it comes to potentially putting together remedial action plans, options appraisals, remedial method statements. And then again, likewise, Lawrence has a fairly substantial experience in different remedial techniques. So I trust with Lawrence and Pete presenting the next piece that you should be in good hands. So with that, Pete, I'll leave it to you, and hopefully we'll get some questions at the end.
Thanks, Rich. I'll turn the camera off while I'm giving the presentation. So yeah, quick bit about RemedX. RemedX is a specialist complete remediation solutions business, was acquired by RSK Group very early after the formation of the group itself. We're a specialist remediation company with a strong focus on technical, innovative groundwater remediation solutions, but we do also undertake a range of enabling works, some of which I'll actually touch on a bit later in the presentation, which, to be honest, of course, is more a function of the landscape of remediation contracting these days. Very rare that one is just given a remediation project with remediation work in isolation to do these days. And we also own and operate a large fleet of our own remediation equipment, along with our sister brand, GRS, which, in a slight change from RemedX itself, focuses on remediation plant hire. Now, just a bit of background on this project. A multinational client with operations all over the UK. The site itself is in the western UK, and the site's been operated for well in excess of 50 years. The focus of the remediation works themselves are the cleanup of EDC, ethylene dichloride, or 1,2-dichloroethane. Although technically there's no actual remediation being undertaken by this contract. The scope of the contract itself was to actually effectively introduce the reagents, and slightly confusingly, that reagent is called EHC. So bearing in mind, a key distinction to bear in mind as we go through is the acronym of the contaminant EDC versus the acronym of the reagent EHC. Anyway, the reagent will facilitate the remediation basically by delivering it to the right location and depth within the underlying geology, more of which next. It's worth mentioning, as we come on to the geology, the properties of EDC itself, it being a chlorinated solvent denser than water, very highly soluble and very persistent in the environment. So these cross sections, the geological cross sections, were produced by the client's consultant using a range of, historic site investigation data and data collected from our own baseline site investigation. And what I really need to, or want to get across, is the very complex geology underlying the site. Bearing in mind the reference I made to the properties of EDC that I mentioned on the last slide, you can kind of see here how pockets of contamination would potentially lie in high transmissivity sands and gravels, the yellow layers, bound by lower permeability silts and clays represented by the green. But also follow the topography of the geological boundaries and essentially migrate towards the river which bounds the east of the site. And certainly a significant component of the work comprised protecting the river from the accidental mobilization of EDC and indeed co-contaminants towards the river, the mechanism of which I'll discuss in more detail a little later on. So onto the remediation works themselves, or the installation works themselves. The main objective is principally the biological reduction of EDC, it being the most effective treatment mechanism for that specific contaminant. But of course, there'll be other processes and other contaminants that may be present, treated by the works themselves. Now, the method of introducing the reagents into the ground was selected was deep soil mixing, and that was used to get the EHC to the correct depth across the correct impacted thickness in each of the soil mix column locations, each column being 900 mil in diameter and roughly between 5 meters deep in the north of the site and a maximum of about 14 in the south. We designed the column spacings, more on which later from Lawrence, based on the EDC concentrations identified by the site investigation works in cells of 100 square meters that we divided the site up into. I mean, and objectively, really, the EHC dosage, the variable EHC dosage per column was designed to both treat the EDC concentration in situ and beyond, but also to achieve performance criteria, that one of the requirements being a representative dose of 1% of the reagent across the entire contaminated mass of soil. And it's important to note that because, of course, not the whole soil volume was mixed, we were reliant on a number of other factors to address this criteria, and those factors I'll come on to shortly. So just going back a step towards the protection of the river from upwelling contamination migrating through those high transmissivity sands and gravels, we provided a hydraulic control system comprising the water treatment plant that's pictured on the slide, together with a cement bentonite cutoff wall constructed from, again, 900 mil overlap columns with 3 meter wide gates, for want of a better phrase, at the location of each hydraulic control well. This wall was installed along the whole site boundary with the river, which was about 50 meters or so. The gates are present to prevent groundwater upwelling post-remediation, which is to say when the systems switch off, given that the wall itself will remain in situ. And they were designed to be bridged in operation by the radius of influence of the hydraulic control pumping wells, based on modeling from pumping tests early in the project. So what is EHC and how does it actually work? It's a proprietary product from a company called Vonic, and it was delivered to us in 25 kilo bags as a dry powder, comprising the constituent components listed there. And the process was, it was to be mixed in an air-powered mixer with water on site into a pumpable slurry containing various percentage doses, more of which later on. And the principal mechanism of treatment we were concerned with here with respect to EDC remediation is the stimulated biological reduction. Inevitably, of course, direct and indirect chemical reduction will take place and the thermodynamic decomposition. But in fairly simple terms, we're looking to the reagent to degrade in situ and create favourable conditions for microbial reduction of EDC. So what we're sort of really leading into now is the sort of physical design of the works, which basically took advantage of this treatment mechanism specifically to drive efficiency of the reagent delivery and efficiency in terms of the overall project cost. So again, taking advantage of the mechanism of action and the treatment of EHC actually allowed us to vary or flex the column spacings across the site in response to EDC concentration. Originally, the specification for the project called for overlapping columns, which is to say mixing the entire volume on site, which had a high cost, would have been very difficult to implement and essentially inefficient in terms of making the best use of the aforementioned treatment mechanisms of the reagent. So in order to make the project more budget feasible and practically workable, we took advantage of what's referred to as the halo effect. So what is that? What does that mean? Well, again, put simply, it's a zone of reagent degradation products in the groundwater extending down gradient of the directly mixed soils. And what this functionally means is that you can afford to not mix the whole soil volume, the whole impacted soil volume, being reliant upon a little time, several weeks in fact, to induce strongly reducing conditions in the aquifer, which effectively bridge the gaps between the mixed soil, the columns themselves, eventually making the entire impacted zone a strongly reducing reactive zone through which groundwater could flow. And EDC solubility is so high that we were also able to take advantage of concentration gradient driven movement of EDC from unmixed areas to mixed areas for direct reduction. Now, what's actually happening with the biological reduction itself is that the organic carbon component of EHC ferments in situ and produces volatile fatty acids, which essentially serve as electron donors for microbial reduction, but also buffer the pH down, which reduces precipitates in the zero valent ion and which allows the maintenance of reactive surface availability in the zero valent ion for direct reduction. And alongside this, other reactions are taking place. Ion oxidation and carbon fermentation consumes oxygen, further improving thermodynamic conditions for dechlorination. And the ion corrosion itself leads to hydrogen generation with a resultant high electron or hydrogen ion pressure, which is again favorable for thermodynamic dechlorination. Just a couple of illustrations. These figures were to illustrate the sort of spatial distribution of the EDC on site. These figures were again produced by the client's consultant using a mix of the historic and RemedX SI data, and just give an overview of the pre-works condition of the site in terms of the concentration in soil. What that translates to in terms of significance of EDC mass in the cells was divided up into for the works. And finally, what that means in terms of the impacted thickness. It's worth pointing out that the impacted thickness, the diagram on the right-hand side of the slide, is not the depth from the surface, it's the actual impacted thickness that was required to be mixed and co-mixed with EHC. So total mixing depth would be in the order of 14 meters, including overburden for the southern area of the site. So I'll hand over to Lawrence now to talk about the column designs themselves and the sort of technical implementation of the work. Lawrence, thanks.
Thank you, Pete. Yeah, so I'm just going to talk a bit about going from the sort of contamination profile through to a actual column specification to implement, really. So first box here that just shows some of the initial designs in terms of treated volumes and of soil. 1B was the original design, which had about just over 5,000 meter cube of soil that needed to be targeted. There was a revision 1B Rev that was completed or revised based on additional SI. This significantly increased the amount of impacted volume that needed to be targeted. You can see it also pushed the number of columns required up, and it moved into the realms of being not very cost efficient and practical. And as such, it necessitated a bit of a revision of the process and moving towards the column spacing and the halo effect and the reliance on the halo effect, which Pete has already discussed. So based on this, in the process of this revision, it also meant that we moved to a variable dosing percentage and a variable column spacing. So the column spacings in the second table here, the column spacings were varied and the dosing percentages varied based on the soil concentrations, the actual average concentrations in the grids. And based on that, the spacing was derived. So in the most contaminated sections, the smaller spacing was used with a lower dosing percentage. This was because you were actually achieving about a 50% volume of direct mixing, actually taken up within the mixing columns themselves. So you got a lot more direct treatment, and then you were obviously therefore reliant much less on the halo effect. As you spread the columns out, as the concentrations got less, you spread the columns out, which necessitated an increase in the dosing percentage for EHC, because you're only targeting down to about 20–23% of direct mixing. So it therefore becomes much more reliant upon the halo effect at that point. Pete, you can move on to the next slide. So what does this actually mean in terms of an actual final design? So this graph just shows, or this plan just shows, what was the actual final derived column schedule for this site. Ended up being 925 columns in total. We ended up, and you can see that the different colors here correspond to different spacing and dosing percentages that we used. The light blue being the most spread out and the less contaminated grids, the green being the sort of moderate ones in the most contaminated section. The smaller spacing is the orange in the center. There were a few sort of, I guess, final amendments that were required to the, going from the theoretical schedule to the practical. We had a couple of restrictions on site, as there always are. So down the left-hand side, we had to, due to a newly installed service that was put in by the client, we lost a couple of meters of accessible ground on the western part of the grid. So we had to modify the dosing percentages on that side for that. You can also see that there is a sort of a dark gray voided out section that runs through the center. Again, this was another service, a concrete service that was present, which would not have been able to have been, while a redundant service would not have been able to be drilled through. So that meant we had to offset the spacing of columns around that for a couple of meter standoff around that. And finally, also over on the eastern side of the site, there was some very steep topography coming down to river channel, which just meant from a practical and health and safety point of view of doing the installation, it wasn't practical to work in such close proximity. So again, a bit of an adjustment for some of the columns in that area. Another thing to note as well is you can kind of see the topographic contours on this map. There is quite a large change in levels across the site, which did facilitate installing the columns across a couple of levels of piling mat, which will be demonstrated a bit better later in the presentation. So moving on now, this graph is, so this is a actual 3D model of the actual installed column grid. This is just this sort of dark shaded is just showing where it's getting darker, is showing where more of the soil mass targeted is, and where it's lighter, there's less basically. So this just gives you a bit of a sort of feel for the 3D nature and the actual distribution of where the EHC was implanted. And if we move on to the next. And this one also then shows, so it's the same grid, but this is showing the actual dosing percentage for the actual columns, and you can quite clearly see the actual different dosing percentages that were achieved across this grid based on the, again, the original EDC concentrations. So moving on to, in terms of in the process of actually implementing the works, the sort of validation criteria for the works was the sort of implementation of the 1% average EHC across the plume essentially, and therefore it was a quality control exercise to ensure that that was achieved. And so this was kind of done through a few different mechanics during the works. The first one was bench mixing. We did some bench mixing trials to determine what the best actual slurry mix percentages were to use for this job. Again, it was based on the reagent is slightly different to a standard sort of deep soil mixing bentonite application or foundation application. So trials were run to determine what sort of workable materials were, which then informed the actual column specification design. Then during the actual works, there was a sort of daily process of logging the daily completion to track the actual progress and completion of the works, and then there was also a subsequent review of digital the digital log output. So the rig itself has a number of metrics which are tracked during the operation of the works, including rotation speed, how much volume is injected at certain depths, and also target depths and actual volume, an actual volume of the slurry as well. So the sort of quality assurance was a case of reviewing these drawings, and it allowed us to inevitably, over the course of 925, if there were, or as and when there were, the odd mistake or issue or error, it allows you to adjust and correct the schedule to account for that, to make sure the correct works were delivered. Another part of this work which was used to help with the validation was the use of drone surveys, which is useful for tracking the actual installation locations, and also obviously for surveying and making sure that the columns were laid out and installed correctly where they should be. And then obviously, as with all remedial works, it was subject to deployment of a license and the monitoring of the environmental parameters that go with that, including noise, dust, odor, vibration, VOCs, etc., on top of the standard health and safety concerns that also go along with these sort of works. So yeah, that kind of brings a summary to the end of the technical assurance side of the installation.
Thanks, Lawrence. I thought it would be useful at the back end of the presentation just to put up some images of the works and really give you an idea of what this actually functionally looked like on the ground. So this image is the piling rig basically getting ready to install the bentonite cement cut-off wall. The mixing head's not actually attached to the rig in this picture, but you can see, or you can just make out to the sort of far bottom right a line of yellow sort of mushroom head covers on top of pins. Each of the pin locations is a column location for the cut-off wall, which was installed between the hydraulic control wells with the black pipes in and the silk fencing that you can see in the background. The method of installation was basically install one, miss one, install one, miss one, and then going back up the line and reinstalling as the cement bentonite columns cured. The red piece of plant in the middle of the site, in the middle of the picture, is one of the slurry mixers, just for reference. This is an image of column number one being installed. It was quite a long haul through various different designs, repricings, and not sure if you're aware of the pandemic, to actually get to this point. So it was a pretty momentous day, to be fair, to actually get column number one in. And again, you can see in the sort of center left of the picture. The telehandler is basically offering a pallet of EHC to the mixer to be mixed into the slurry, which is connected by the pipework to the rig head. So I mentioned at the beginning of the presentation about the enabling works aspect earlier on. There was quite a significant component of this project that was basically a civil engineering exercise in order to facilitate the remediation works themselves. And it is worth mentioning the huge effort that went into the temporary works design for slope stability reasons, and also the working platform design to make the site safe for the rig to operate on and for the deep soil mixing to be undertaken. Ground conditions were actually pretty poor, and this is just a good example of sort of our capability in terms of actually undertaking these enabling works, having the flexibility to undertake this sort of operation alongside the sort of traditional work that we do of the technical remediation. This slide in particular, what I want to really sort of illustrate is something that I don't think anyone had really anticipated at the outset of the project, which is the amount of water consumed by the soil mixing operation, and also the resultant surface slurry that arose from washing out the lines after each location, and a small amount of soil and slurry displacement at the end of each column completion. What this actually meant in practice is that we ended up having to construct quite a significant slurry management system, on particularly on the lower previously mixed part of the site by this stage of the works, which was really to prevent the majority of suspended solids reaching the hydraulic control system and choking the system. The system ended up being more a surface water management control system than an actual hydraulic control system, really, in terms of volume. But this just shows you just how much slurry was running off. This next slide as well, you can see here the clear difference between the soils on site and the red-brown slurry running off the working platform into the management system. Of course, it's the colour it is because of the iron oxidizing rapidly, and although you can't tell from this image, it also has a very strong characteristic organic smell from the carbon fermentation, which happens quite quickly, alongside the stark colour change. So as Lawrence mentioned, we used drone surveys quite extensively through the job. Just thought I'd throw up some of those images just so that you could see the evolution of the site. And the image is from, this image is from quite early in the project. You can see the piling rig on the right hand side installing the cut-off wall columns, or preparing to, in fact, and the excavator in the middle there, the orange piece of plant, prepping the initial working platform for final testing. You do get a sense here as well of the actual space constraints on the site. It wasn't the most spacious site in the world to work on. And we're part way through installation here. You can see the installed columns as the sort of brown circular dots on the ground by the roller, the yellow piece of plant in the center of the site, and the red-brown slurry stockpile there by the HCS, which was all of the slurry that was gathered up from the phase one of the column installations. We're prepping the second working platform here, but you get a clearer sense of the density of the column installation, again from the dots that you can see on the ground, particularly there immediately to the south of the roller. And here we are at the sort of tail end of the column installation program, with the piling rig working across the southern area of the site, and a clear presence of the slurry I mentioned at the surface, both on top of the working platform and running along a drain that we excavated across the sort of southern site boundary there, just beyond the piling rig, which runs down towards where the excavator is in the middle right of the image. The grey slurry that the excavator's in is fresh, unoxidized slurry being managed through the management system, with the resultant solids eventually being excavated out and placed in the slurry lagoon, which is very obviously the red-brown area in the rough center top of the image there. Water then drained around into a silt trench through a series of bonded areas to a silt trench along the other side of the cut-off wall, and the water then pumped into the HCS, treated and discharged. So that completes the presentation, and Lawrence and I would be happy to answer any questions, and by all means take a note of our contact details for any other questions, inquiries, or getting in touch. Thanks very much.
Thanks, Pete. Thanks, Lawrence. Really good. Really interesting to learn about and listen about that. Got a few questions. So this one's actually come in a couple of times. How and why was EHC selected as the preferred reagent product? I don't know, Pete, Lawrence, one of you two.
There's a short answer to that, which is that's what we were told to use.
Okay.
So that was prescribed to us. Originally, the specification called for a different, again, proprietary product from Evonik called Daramend. And Daramend is basically the same as EHC, but doesn't contain the emulsifier. And so it's not specifically designed for deep soil mixing, whereas EHC is. It also contains, generally speaking, coarser zero valent iron, so it would have potentially caused more blockages of the nozzles on the deep soil mixing unit. But that was part of the specification. Was the reagent was given to us as part of the spec.
Okay, I mean, that also leads on to another question, really, in that we've been asked about lab trials. So, I mean, Lawrence, I think you mentioned about lab trials. So if the reagent was specified, what was the reason for the lab trials?
So when I say trials, they were bench scale trials, but this was more practical. They were testing the actual practical mix of the slurry. So it was more to do with the physical pumping and distribution and injection of the actual slurry with the rig, rather than it wasn't validating or testing the actual remediation, the remediation effect itself, if that makes sense. It was more for the actual installation, so to make sure that it was actually distributable to the ground and to the subsurface with the equipment we've got.
Okay, no, fair enough. Another one here, someone's asked, what was the driver for the remediation on site? Was it a planning requirement, i.e. to make suitable for end users, or to stop contamination to the watercourses? They've very politely said, sorry, they may have missed that early on, if that was discussed. So what was the main driver for this?
No, it wasn't discussed, and principally it's the protection of the watercourse, yeah.
Fair enough. Okay, another one we've got here is, you mentioned, but it says here, how did you manage targeting the impacted zone versus overburden? I assume from that what they're saying is, because I think you mentioned earlier in one of your slides that there was a varying thickness, wasn't there, against an overburden on top. So how were you able to, I guess they're asking here is how were you able to determine where you were mixing? Was it through just basically using the rig to measure depth, or?
Yeah, I mean, so there were two elements to that. There was, first of all, there was actually coming up with the quote unquote recipe for the columns, which was based on historic SI data. It's easy to just sort of gloss over a statement like historic SI data. There was a huge amount of historic and more recent site investigation data, which basically led to underground or subsurface topographical mapping of the depths of those geological interfaces, which through an assessment of the EDC concentration identified what that thickness should be at the column design stage. Then in terms of the rig actually getting the EHC to where it needed to be, well, Lawrence, maybe if you pick that one up.
Yeah, so based on the model, for each column was obviously given a location spatially, and then that location was then interfaced with the profile, the contaminant profile, which then generates the sort of top and bottom depth essentially. That was the case for the bottom of the bottom surface of it. So that was a surface, and each column had its own unique depth. The top surface was done on an average basis based on the grids themselves. And then how it was actually confirmed and tracked was the rig is, or knows how deep it is. It has a constant logging of its depth. So once you've essentially derived the recipe, as Pete referred to it, it's just a case of making sure the rig hits those depths then. And in terms of the overburden, because obviously there is anywhere from sort of like 3 to sort of 5 meters of overburden in all cases. So that was a case of it was over drilling through, water was used to flush through the rig at that point. And they had the mixing tank set up so that once they get to the target depth, they can then swap to injecting the actual slurry itself, and then that'll be injected through the profile, and then when they're coming back up, they just flush the water again up the top through the overburden essentially.
Okay, thank you. Good few questions coming through now. So we've got one here that says that the cut-off soil concentration of 77 milligrams per kg was applied for defining the area where to mix. Was there another remediation technique being used for other parts of the contaminated area? Because that's a high soil concentration, it can still leach and produce a large plume.
No.
No, I think the answer to that one is no. I mean, that comes down to Pete, as you mentioned before, isn't it? That this was we were given the design, weren't we? But the specification by others. It's
difficult to. I mean, this is one part of a much broader site remediation kind of master plan that is happening for that particular site. And so this is one part in isolation. There are other things going on that will affect and to take away from this particular piece of work. Again, it sounds like I'm sort of going around the edge of what was actually done, but the actual remediation is not part of this contract. What actually happens in terms of the treatment is not what we're contracted to do. What we're contracted to do is put the reagents where the reagents are supposed to be, and that's basically the scope of the job.
Okay, thank you. Sorry, just another couple of questions. So there was mention of environmental licenses. Which ones were required for the works?
Yeah, so yeah, this was we deployed a mobile treatment license for this, so it's a pretty standard remediation license that allows you to do a whole range of different remedial techniques. So yeah, and there was an existing discharge consent for the water treatment plant that was owned by it, which was held and owned by the site and still was. So we just utilised that with modification to it. So yeah,
we didn't need an abstraction license because the amount of water we were taking out the hydraulic control was below the threshold for one.
Okay, we've got two questions here that are fairly similar in fact. Have the remedial targets been achieved? And if so, or if not, what ongoing monitoring is required to check that it's worked or is working?
Well, there's a very short answer to that, which is that the remediation will be taking place over the next 10 to 12 years and does not form part of our responsibilities to monitor or ascertain the success thereof. The verification criteria for this project is simply the correct installation of the reagents to the correct depth. Others will actually monitor the ongoing remediation work and the successful achievement of the validation criteria, the target criteria that the client's working to.
I think on this particular project we were much instructed to do a certain task, and that was it, wasn't it?
Yeah, it's a bit of a weird one because, as I said at the beginning of the project, I mean, obviously I've been involved in a lot of remediation projects over the years where we've actually done remediation, achieved the goal, and ridden off into the sunset, and everything's fantastic. But That's not the case on this job. The remediation itself is going to happen after we've gone for a period, another decade beyond the installation phase. I mean, that the direct and to some extent indirect reduction is going to happen quite quickly, where we've actually mixed reagents into EDC impacted mass in the ground. But the production of the halo effect and the longer term protection of the river and the creation of the reactive zone, that's going to take time. And the actual sort of throughput of the contaminant mass as it flows through the reactive area, that's going to have to be monitored over the next 5, 10, 15 years.
And that's been done by others, I assume, isn't it?
Yes.
Yep.
I don't know who.
Okay. Aware we're coming near to the end of the talk. This may be a long answer, so we may not be able to give a full answer here. But we've been asked, can you give any information on the hydrology? Was the permeability significant, and did you rely on groundwater flux to achieve coverage in the halo, or was that dependent on diffusion?
Not a hydrogeologist. Some of those words are just foreign to me.
I think what we'll do to the asker of that one, we'll come back to you offline on that one with the kind of a bit more detail on the hydrology. As Pete said, we had a consultant on board who was very specific with the specification, what was required, and we, as much as we do provide that ourselves on this occasion, we were kind of asked to do really. One last question, and which is, are we able to provide any indicative costs for the project?
It was less than 5 million quid.
Thank you. All right, that was short and sweet. Thank you. One last one. Will they have to pump groundwater for all the time it takes for the remediation to work? That's just come in now.
No, the hydraulic control system was just there as a kind of insurance mechanism against the possibility, the very slim possibility of a high concentration band of EDC impacted material being displaced by the soil mixing. In actual fact, the soil mixing head it's not like a continuous flight auger that displaces soil from depth to the surface. It essentially mixes and homogenizes in situ. So the chances of that actually happening were fairly slim. But the idea of the hydraulic control system was to prevent any fast throughput through the high transmissivity soils that might have a point source discharge to the river, basically. Now, post remediation, we want the groundwater to flow through the reactive area and continue to carry those degradation products and indeed the reducing conditions down gradient beneath and up well to the river. So you actually want that to happen, which is why those gaps are in the cutoff wall for the water to continue to flow. So in short, no pumping will carry on post installation.
Okay, thanks, Pete. We're going to have to draw it a close there. We've run out of time. So there was one question there on the geology, which we'll come back to off the call. But thanks for the questions, a good set of questions there. So thanks for the participants for dialing in. Trust you found it useful. As I say, if you want to go back to Pete or Lawrence specifically, then please do. But otherwise, thanks ever so much indeed. Thank you.
Thanks.